Okay, so we'll begin with lecture 40, which is the last lecture of this course, in which we will primarily discuss about 2D defects, which is the remaining topic of this course. So what we did in the last lecture was, so we introduced we introduced defects in the last few lectures, 2 lectures, and we first talked about the point defects, which are equilibrium defects, which means they are thermodynamically stable as a function of temperature. Except at 0 Kelvin you will always have point defects in a material, and point defects are basically, you can say, vacancies, interstitials, substitutional atoms, and so on. So these are primarily 3 point defects that you see in the materials, and the concentration of these point defects varies as a function of temperature. So basically this is the defect formation energy, and higher the defect formation energy, lower is the defect concentration going to be, and which is a function of bond energy typically. So if bond energy, materials with higher bond energy will have lower point defect concentration as compared to materials with lower bond energy, and you can see that it has exponential dependence on temperature, -1/T. So as a result, when temperature increases, the vacancy concentration also increases exponentially. And then second defect that we considered were line defects or 1D defects, and here we looked at edge dislocation and screw dislocation. So essentially an edge dislocation was an extra plane of atoms which has been put in a otherwise perfect lattice. This extra plane of atoms is useful in the sense that it allows the materials to deform. It also creates its own stress fields. There is a tensile and compressive stress field in the 2 parts of the lattice, and the dislocations, this dislocation can be characterized by its own Burgess vector. So if you look at the edge dislocation, if I go to edge dislocation, so if you look at the top view of edge dislocation, this is the plane in which you have a dislocation line. This is the dislocation line. So vector is T, okay, this is top view, okay, and the Burgess vector is along this direction. So this is B vector, all right. And when you apply stress, I will show the stress relation with the stress in the next slide. If you look at the side view is something like that. So if this is the crystal, okay, so here you have an extra row of atoms. These are the other rows of atoms. So I am just making them solid lines, and so this is the perpendicular. So perpendicular to the plane is this T vector. So this is side view or front view. So T is normal to the plane of the paper. So this will be going into the plane, and the Burgess vector would be this. And as you apply stress, shear stress, this will slowly move out on this side and giving rise to a step. So obviously you had a step on this side, and this will create, when it moves out completely, it creates a step on the other side, leaving a relaxed crystal. The magnitude of that step will be equal to Burgess vector. So in this case, as you apply stress in this direction tau, and the T moves, the dislocation line also moves in the same direction as of stress in Burgess vector, but dislocation line is perpendicular to the stress as well as the Burgess vector, okay. So this was edge dislocation, and then we looked at screw dislocation. which was basically you had, this was one part of the crystal and the second part of the crystal was slightly sheared with respect to, so sort of sheared in this fashion. So this is a sort of shearing that takes place. So this I can mark this as red. So red one is top part of the crystal and blue one is the bottom part of the crystal, and top part has sheared with respect to the bottom part with respect to quantity called as by an amount quantity Burgess vector, and this is the dislocation line in this case T, whereas the other part of the crystal is like this. This is the remaining part of the crystal. Okay. So the 1/2 of the crystal has sheared. So when you apply stress, so in this case the stress is applied in this direction, this is stress. So stress T vector and V vector, all of them are parallel. So when you apply stress, this dislocation line will move in this direction, okay, eventually giving you a step which is like, so this is the top part and the bottom part will be like this, or this is the top part and that is the bottom part. So this is a step that you create, one step here, another step there, okay, after the application of stress. So in this case, in the screw dislocation case, your B was parallel to T and B was also parallel to tau, and T moves perpendicular to the stress direction, right, whereas in the previous case B was perpendicular to T, B was parallel to stress, T was perpendicular to stress, T moves in the direction of stress, okay. So these are the take home messages. I will just show you sort of animation in which you can see this. So this is sort of the, so here you can see this is the motion of edge dislocation. So you had an extra row of, you start with an extra row of atom on the left. So this is an extra row of atom. So this is the extra row of atom you had. When you apply stress, it moves to right. So now it is here. After some time it is here and then it completely moves out of the crystal, okay. And this is how the edge dislocation moves in this case, and the screw dislocation on the other hand moves in a different manner. So when you apply stress, so this blue, so these blue ones are the stress arrows. So this is the dislocation line, the one in the orange, it moves in this direction, whereas stress is in the it's in this axis. So as you keep applying the stress, the line moves of the crystal, giving rise to steps which are here. This is one step, this is second step. Somehow the color is not coming very well, but this is how it moves in the screw dislocation, okay. So this is sort of the summary of two dislocations. In edge dislocation, B is perpendicular to T. In screw dislocation, B is parallel to T. The relationship between line vector and Burgess vector is, in edge dislocation it is perpendicular, in the screw dislocation it is parallel to the, so B and T are perpendicular to each other in edge dislocation, whereas B and T are parallel in screw dislocation. The slip direction, the direction along which dislocation line moves is parallel to Burgess vector in case of edge dislocation, is parallel to Burgess vector again in screw dislocation. So movement is parallel to Burgess vector in both the cases. The direction of dislocation line movement with relative to Burgess vector is parallel to Burgess vector in edge dislocation and it is perpendicular in the screw dislocation. And finally, I just wanted to show you the type of Burgess vectors in cubic crystals that you see. So, the translation of Burgess vector is always from between two lattice sites. So, it is from one site to another site, identical lattice sites. Okay. So, for monatomic face centered cubic crystal, it is half 110 axis direction, and monatomic BCC it would be half 111, monatomic simple cubic it will be 100. For sodium chloride it would be half 110 because it is FCC lattice. However, for a cesium chloride structure it is 100 because there is a cesium atom sitting at simple cubic position and chlorine atom sitting at simple cubic position. As a result, the vector is of simple cubic, although structure looks like BCC, it is not some BCC. Diamond cubic again is FCC structure, for this it would also be half 110. So, it has to go according to crystal system, okay, not just the position of atoms. So, it has to move from one identical atom to another identical atom, and they have to be one lattice point to another lattice point. Okay. So, complete lattice translation basically. So, this is where we finish the edge dislocation part. We will now take up the surface defect part of the remaining. So, now we will introduce what we call as is surface defects or 2D defects. Now, basically these are any kind of interfaces or surfaces in the materials. So, for example, you can have grain boundaries, you have, so first defect could be your, so if I list them out, your grain boundaries, then you can have stacking faults, then you can have twin boundaries, and you can also have grain boundaries can be both low angle and a small angle depending upon the angle of mesh orientation, and basically the free surfaces. Okay. So, and there are many more other examples of, and basically any kind of interfaces. Okay. Interface, it could be it could be interface between the two same materials, it could be interface between two different materials, and so on and so forth. So, let us just go about this one by one. So, grain boundary basically means, suppose you have, as I explained in the last lecture, suppose you have this volume of material. So, let us say we have, so what could happen is that in this part of the crystal you can have atomic arrangement like this. Okay. In the other part of the crystal, your atomic arrangement could be so basically they are not closed pack atoms, they are stacked in a fashion which is slightly different from the previous one, or it could be same orientation, it could be closed pack layer oriented differently. So, this is another kind of orientation. You can have orientation like this, and you can have another orientation somewhere here. So on and so forth. So, you can see that one, if you take a particular vector, let us say this is the closed pack direction in this case, this closed pack direction in this case lies in this direction, in this region it lies in this direction, in this region it lies in this direction, in this case it may lie in this direction. So, as a result these they create boundaries between them, which are the regions of misorientation, where the orientations do not match. So, these are the regions of you can say crystallographic misorientation, and this is what. So, the region in which the orientation is all same is called as a grain, and this is called as a grain boundary. Now, depending upon the angle of misalignment, these could be called as high angle or low angle grain boundary. So, grain boundary can be further categorized as low angle or high angle. So, if I show you the now images of these two samples. So, this is what it would look like if you look at this image. So, here this is one region in which all the atoms are arranged in one manner, this is another region in which atoms are arranged in another manner, and this is one region, this is atoms are arranged in one particular manner. So, if I take so this is the direction of, let us say, closed packed direction within this plane, and this is the direction within this grain, and if I calculate the angle between the two, I get the angle of misorientation. So, you can see that between the grain on the left and the right, the misorientation angle is smaller. So, this is the angle, let us say theta, and between these two. So, if this is grain 1, grain 2 and this is grain 3. So, between grain theta 1 3 is smaller than theta 1 2. If I take the same direction in grain 2 and grain 1 and then calculate the angle, this angle is larger. Okay. So, this grain boundary will be called as high angle grain boundary, this would be called as low angle. I will come to the magnitude in a short while. And if you look at the grain structure of materials in an optical microscope, to look at to visualize this, you need to normally subject the material to a acidic treatment. Okay. So, which is called as etchant, use of etchant. So, basically this etchant is nothing but a mixture of few acids, dilute acids, which preferentially removes the atoms from the grain boundary area, because grain boundary is a loose part of the material, it has higher energy. So, it gets etched preferentially as compared to the grain. So, when you subject it to optical microscopy, the light gets scattered more at the grain boundary than at the. So, there is more reflection from the grains than at the grain boundary. As a result, grain boundaries appear darker in comparison to the grain. So, the region which are dark are the grain boundaries, whereas regions which are bright are the grains. And the grains may also have different color, because different color represents different may represent different phases as well as different orientation of grains. So, depending upon the crystallographic orientation of the plane, the reflectivity of the plane itself may be different. Okay. So, but in a normal optical microscope, you see this black and white contrast. The white ones are typically grains and black ones are the black boundaries are called as the grain boundaries. So, these are grains and these ones are the grain boundaries. Okay. Basically, one uses an etchant to preferentially remove atoms from the grain boundary, and as a result more light is reflected from grains than grain boundary. And these grain boundaries are region of misorientation. Basically, they are an interface. So, as a result, every grain boundary is associated with a grain boundary energy. okay, energy which is in joules per meter square, gamma GB. Okay. So, typically a higher angle grain boundary will have higher energy as compared to a lower angle grain boundary in the materials. The angle of misorientation between the two is typically about, so the way you define them is if theta misalignment is less than nearly 10 degrees, it is called as low angle grain boundary, and if theta misalignment, I think it is about 9 to 10 degrees, if it is greater than 9 to 10 degrees is called as a high angle grain boundary. Often in many materials the low angle grain boundary can be viewed as an array of dislocations. So, basically what happens is that there is a atom to atom correspondence up to certain distances and then it breaks off. So, if I would like to show you an image of that. So, this is how a low angle grain boundary looks like. So, here B is the Burgess vector, H is the height between the distance between two dislocations. So, as if, so this is you can say the grain, so this is number 1 grain, this is number 2 grain, and they are oriented in such a fashion that there is atom to atom contact at various places. Only between the dislocations you seem to have the atom to atom contact missing. So, it is like an array of dislocation, this is like a vertical array of dislocations. Okay. So, they may have some strain at the interface, but atomic density at the interface is higher than the high angle grain boundary. So, this defines the net energy of the low angle, high and low angle grain boundaries. So, these are two energies, these are two grain boundaries that we talked about. Now, the second thing is called as stacking fault. Now, stacking fault is something which typically is observed in close packed crystals. You can say it is typically packed structures such as nickel, copper, and basically it is a disturbance in the atomic stacking. So, we saw that in FCC structure, for example, you have ABC kind of packing. So, you have A plane, you have B plane, you have C layer, so on and so forth, right? A, B, C, A, B, C, and they are all same atoms. Now, suppose if I introduce a stacking fault, it may appear something like this. So, you have A, B, C, you can have after C it can be just, so C, A, B, then again A, then again say. So, here if I just mark it, you have A, B, C, A, B, then again it could be A, B, A, B before it becomes ABC, ABC again. So, you have this region of the crystal which has different stacking as compared to the previous one. So, here you have ABC, ABC, but you end up having a stacking which is AB, AB kind of stacking in some region of the crystal. So, this is the stacking fault. So, this stacking fault obviously it is again different stacking sequence as opposed to the normal stacking sequence in the materials. The thing about stacking fault is that since it happens in close packed crystals, there is no change in the number of nearest neighbors. So, whether it is AB, AB stacking, whether it is ABC, AB, ABC stacking, the number of neighbors for each atoms remain 12, there is no change in that. However, what it changes is there is a shift in the so if you look at, for example, this layer, so all right. Okay, so that is how you form that. So now let us say I have two kinds of voids here, right, A and B. So now let us say the second layer of atoms, it goes here, one on here, second on here, third on here. Okay. Now somewhere, so these kind of voids, they are used for basically I am not filling these voids. So these are for the next layer. So let us say this is the layer A, this is the layer B, or it could be BC or whatever, right. Now suppose the next layer somewhere in the crystal, so I can see that which voids are empty, not covered, these are not covered. Similarly, you will have these are not covered, these are not covered. Now somewhere in the crystal, let us say I start having an atom sitting here. So I can see right now the orientation is 2 atoms up, 1 atom down, and so on and so forth. In this case, the site which I may want to fill is this, this. Okay. Now you can see what happens between the two of these layers. There is a region of disturbance, right. They have to accommodate in such a manner so that they maintain the packing of the layer, but at the same time they have the two orientation have to fit with each other, which means this is let us say AB, this is AC. So AB and AC, so B and C layer, B and C stacking have to accommodate themselves within the same layer. So as a result there will be a shift in the translation within the layer. So as a result there is a shift vector. So basically within a layer you have to identify them using a shift vector. So if you bring it closer, this layer will basically get shifted by a vector in the previous layer, in the next layer, and this as a result you need to identify using a shift vector to depict the shift in stacking. Okay. So you are going from A, B, C, then you have A, B, A, B. Okay. So the moment you go from A to B, the B is shifted with respect to C layer, right. So there is a shift vector. So this shift vector will go from this side to that side. This is the shift vector. So as you go from ABC, ABC, ABC to let us say ABC, I can make it BC, okay, and then again ABC. So I can see that so you can see A to B, B to C, and then now C to A, instead of C to A you have C to B. So there is a shift in the position, and the shift in the position is basically from one site to another site. Okay. So this is the shift vector. So this is the shift vector in the first plane. This is the shift position in the first. This is the position in the first plane. This is the position in the second plane. And if you take this, if you subtract the coordinates of the two, you will get the shift vector. Okay. And the shift vector basically happens to be of the type of. So basically it happens to be type. I think it's 1/6, 112. So essentially what happens here is the full dislocation gets broken into two parts, which is called as partial dislocations. Unfortunately I cannot go into partial dislocations in this course, but basically one full dislocation, which is half 110, gets broken into two dislocations of type half of 211, and if it is 110 then obviously it is going to be 1/6 21 bar 1, and this would be 1 by 6 1 2 bar 1 to 1. So this sort of reaction will occur. So basically a stacking fault would look something like this. Within the layer you have a stacking fault somewhere in. So this region is stacking fault. Faulted region. This is unfaulted region, and between the two they have these vectors, which are basically partial dislocations which correlate the two regions. So anyway, this is used for plaster deformation, but I just want to tell you that there is something called as stacking fault in materials, which is present, which is useful in deformation. So basically it is change in the layering sequence. Now next thing that we have in crystals is called as twins. So you can have for instance I can show you an image here. So this is how a stacking fault may be viewed as. So this is taken from Professor Anand Subramaniam. So you have the stacking sequence. This is the perfect region of the crystals in which you have ABC kind of stacking, or BCA, ABC, and here you have a broken region BC, AB, BA, AB, and then CA. So this is the faulted region. This faulted region is basically a loop with partial dislocations. So stacking fault is again a surface. It's a surface defect. It has energy of the order of 0.1 to 0.5 joules per meter square, depending upon the type of material. These are called as twins. In twins, basically you have two parts of the crystal. They are misoriented to each other in such a fashion so that across one boundary, which is called as twin boundary, the atoms look as if they are arranged in a mirror like position. So you can see that this atom is mirror image of this atom is mirror image of this atom is mirror image of this atom. So this is called as a twin boundary, and twin boundaries are again useful in deformation. There are two kinds of twins, annealing twins and deformation twins. These boundaries can form as a result of annealing or as a result of deformation in the crystals. Again it's a surface, it has a positive surface energy. So twin boundaries also have energies. Any kind of 2D defect has a surface energy, which is a positive surface energy, whether it's grain boundary, whether it's twin boundary, or whether it's stacking fault. So these are certain twins you can see within the crystals. So this is a twin, for example, I think in the brass, it's in the copper sample. So within the copper sample you can see that this is a twin, and across the twin you have these are the twin boundaries. So these are the twins, these are twins. So these are twins basically. They are not very, they can be sharp, they can be, because the atomic orientation has to be mirror like, as a result these boundaries are typically quite sharp. Okay. And then we have something called as normal surface, which is basically you can say twin is a mirror like. Across the boundary. So it's a surface has and these can be formed after annealing or deformation, and it has a positive energy in joules per meter square. Okay. And then finally we will just look at the surfaces. So any surface, so if you look at the surface of copper, 111 surface of copper, so this 111 surface of copper, each atom has 6 neighbors within the plane, okay. It will have 3 neighbors below the plane, and if there was a next layer present, it will have 3 neighbors out of the plane. But suppose it terminates here, this is the final surface, there is nothing above this, which means the bonds are broken, right, which means the bonds are broken. As a result, there is some positive energy, because creating a surface requires you to break the bonds. As a result, there is a cost to create a surface. So, every surface has a surface energy, okay, because of energy cost to create a surface. As a result, you can calculate the surface energy of a let us say the surface energy gamma s for a surface. It can be calculated, estimated for given surfaces. Now, basically it is related to number of atoms per unit, number of atoms on the surface per unit area, multiplied by how many bonds each atom is making. So, basically you can say it is Nb per atom multiplied by what is the energy of that bond. So, basically gamma b, or we can say Gb, okay. Or Eb, okay, energy of the bond. So, this is number of atoms per unit area, number of bonds per atom, number of bonds broken, right, number of broken bonds, not all bonds, number of broken bonds, and this is bond energy. And since each bond is shared by 2 atoms, you divide it a factor of 2. So, this is basically the bond energy of the surface energy of a free surface. So, here basically this is in number of atoms per meter square. This is basically number, this is essentially you can say joules and per bond, and this is number of bonds. So, you can see that the energy is joules per meter square, or you can say it is called as Newton per meter. Since it is a positive energy, most of the surfaces try to minimize their energy. As a result, surfaces are always in some sort of tension. So, the surface energy of the materials is always depicted in terms of surface tension, okay. So, often we call of it in the form of surface tension. So, there are various materials for which you can have different surface energies. For example, sodium chloride has a surface energy of gamma s of about 0.3 joules per meter square. Magnesium oxide has surface energy of 1.2 joules per meter square, whereas silver has a surface energy of 1.14 joules per meter square. Copper has a energy of 1.64 joules per meter square. So, these are surface energy sort of values of most crystals. They are within the, by and large they are within the range of 1 joules per meter square, 1 joule plus minus 0.5 or so by and large. However, some crystals have lower surface energy as well, which means they can have large surface area, okay. So, this is about the defects. So, what we have discussed so far is you have 3 kinds of defects: 0D defects, which are called as point defects, 1D defects, which are called as line defects or dislocations, and 2D defects, which are called as basically surfaces and interfaces, right. So, among these are equilibrium defects, 0 point defects, but these two are not equilibrium defects. So, their concentration they can be basically, if you take a single crystal, you eliminate dislocations nearly completely, okay. And surface energies, you can make a single crystal, you can get rid of grain boundaries, for example, completely. So surfaces can be minimized. For practical reasons, there are always going to be surfaces, always going to be present, because surface has to terminate somewhere, but theoretically speaking, they are not equilibrium defects, okay. So these are, so what we have done in this course is basically we have covered the aspects related to structure of materials. We started with the atomic structure, where we talked about the bonding in materials, and this bonding and atomic structure led to crystal structure analysis, crystal structure, theory of crystal structures, where we looked at how the atoms are arranged in space, what is the primitive lattice, what is the non-primitive lattice, what kind of crystal systems you have, what are the symmetry considerations, what kind of structures are followed by materials such as covalent solids, and then we looked at the structure of solids basically, right. And in between we also looked at, for the completeness, Miller indices, right. So here we looked at the concept of lattice, the concept of primitive and non-primitive lattice, concept of motif, concept of crystal system, Bravais lattices, concept of symmetry, how symmetry is related to crystal structures, how does it define various crystal systems. Then we looked at Miller indices, interstices in the materials, and then we looked at structure of various solids based on the bonding criteria. So we looked at structure of metals which are metallically bonded, structure of covalent and ceramic solids which are ceramic materials basically, which are mostly covalently and ionically bonded solids, and then we looked at structure of so you can say crystalline solids in this case, right. And then we looked at non-crystalline solids, basically glasses and polymers, which are also technologically important materials. And then we looked at structure determination using X-ray diffraction, and finally we looked at basically defects in materials, because materials are not perfect, they do contain defects, whether they are equilibrium defects or non-equilibrium defects. Defects are reality of life and we need to know them, because they are a lot of times they are useful. For example, point defects are useful in conduction phenomena in materials. They are also dependent, they are also useful in expansion contraction of materials. For a lot of ceramic materials, the conductivity is manipulated by point defect concentration. Similarly, in case of edge dislocation, screw dislocation, they are useful because they allow deformability to metals. Metals will not be able to deform if you did not have dislocations. And 2D defects also useful because surfaces often provide a means for you need to understand surfaces, because most of the materials make certain bond with each other in various application. So characteristics of interfaces are to be known, and interfaces are important because they provide pathways for diffusion, pathways for interfacial reactions. Concept of surface is very important in phenomena such as grain growth and sintering. So any phenomena where there is a large change in the grain boundary area occurs, surface energy occurs, where surface energy plays an important role. It is important to understand the concept of surfaces. So I hope it has given you a brief overview of structure and structure of materials. It's not by all means, it's very it's at the first level. If you want to get into details, everything, all of these topics form a subject in themselves. So you can have a course in atomic structure and bonding, you can have a course in crystal structures, you can have a course in the structure of solids only, and you can have a course on glasses and polymers, as well as X-ray diffraction. So in this course I have tried to give you a bird eye view of structure of materials. If you are interested, there are various references, various books available. You can go through to read in detail about each of these things. So I hope you have enjoyed the course. Thank you very much.